Okay, so good evening everyone. For sake of this NPTEL problem solving session, I am recording this video as there is no candidate. So today I will cover something till week 7, as week 7 has a lot more theoretical part instead of any problem solving things. So my major focus will be on the parsers, which was actually taught in first two videos. Then we will go for some of the uh, previous year questions, and before all of the things I will go for this a revision, a simple revision for what we are covering today. um, that is week 7 content. Let me check something. Okay, so in week 7 the majorly covered part was parsers, some example on parsers, especially on LALR parser and LR1 parser. Then sir has taught about type checking, type coursing, and type expressions. So I will cover. I will first open the PPT and cover the things uh, which are taught. So in week 7, the things mostly covered is actually like this. So in week 7, something which are covered is type checking, then types of type checking, that is static and dynamic checking, then type expressions and equivalence and the conversions. So first a little bit about type checking, which was covered. So it actually deals with the semantic part, and we actually assign some type to the values. So it basically determines whether these values are those are used that is appropriate in manner. So there may be two situations. First is the simplest situation where we check the type of objects and report the type error if there is any error. Good evening, Revant. And in the complex way, there may be incorrect types, and that may be corrected. So that we tell as type coursing. So next thing, there are two types of this type checking. First is static and dynamic. Then in static checking, the static checking is actually done at compile time, while this dynamic checking is performed during runtime of the program. Then the properties that can be verified before running the program, because we are first compiling the things. And in dynamic, uh, there are that is more flexible, we can say. Then static checking basically catches many common errors, but in dynamic checking it is actually mandatory, like array bounds check. And the last one which was told is it is desirable for faster execution, and dynamic checking is for more robust and clearer code. So in brief, the static checking part is actually there for if we want a good code, that has less errors and faster executions. So we will first compile and generate that kind of code and then run. But in case of dynamic checking, we will first we can execute and the checking will be done at runtime. So the code will be more robust, that's for sure, but there may be um, some warnings. Next thing is type expressions. Those are so these are used to represent types of language constructs. So the basic type expressions can be like integer, char, boolean, and all the very atomic types which do not have internal structure. And there is a special type, that is type error, is used to indicate type violations. So there are type names, there are type constructor that is applied to a list of type expressions. Then there is there are some kind of examples which uh, some rules which are provided for it, like if an array is specified like it, then t is a type and I is an integer or a range of integers, like such told if there is some uh, array from 1 to 20, so that is different thing. The indexing will start from 0 to 20, and in this case we will start from 0 up to 99. So and this is one thing. Then there is, if there are two type expressions t1 and t2, then that represents anonymous records. So for example, an argument is passed with first argument integer and second is real. So uh, those two will be um, have type that integer draws real. So I think from here I should take some previous year questions, then we should come on the next things. So let me share the different slide. So coming to the question 1, it is about type expressions. So type expressions corresponding to a function that takes an argument, a function that maps an integer to a character and returns an integer. So what should be the answer if there are two joinees? So I will request you both to, if you can answer. Comment section is open. I think I missed to. No, you are missing a little bit. Oh, one thing I should draw like this. Now that maps integer to character and then returns integer. I think I should I had to cover the next slide also. Okay, no problem. If you have went through the PPTs, then it is a simple one. So it is telling that you have to map an integer to a character and then return an integer. Okay, yeah. So first we will convert integer to character, That is one thing, and we have to return integer. So we have to map this domain to this range integer. Okay, so answer is actually A, right? Then second is a theoretical question. A weakly typed system generally makes the program writing difficult, less error prone, easy but more error prone, or difficult but less error prone. So please comment. Yeah, that is C. So weakly typed means we don't have more restrictions on type. So it is easy, but there may be many warnings and may be more errors. So it is susceptible to that error. Good. The third one, for a strongly typed system. Yeah, that is difficult but less error prone. So if we will pose the types strictly, what will happen that the system will get more and more error prone in that case, but at the same time we have to face difficulty of writing the code. Now coming to the fourth one, when scoping rule necessitates additional code in the final translated program, which is scoping rule necessitates additional code in the final translated program. A is not correct, actually it's B. How? I will cover in the slides. It is actually there in the week lectures if you just go through. um, okay, no problem. Okay, this is a simple one. Type checking checks the input lexically, semantically, syntactically, or all. No, type checking is done for semantic cases. So in lexical analyzer we have just tokens. So what we can check anything. In syntactical analyzer we have a parse tree. So it is grammatically correct or not, that we can check, but the type is actually asserted in this semantic analysis case. So that's B. Yeah, good. For 6.1, most programming languages are weakly typed since such languages put less constraint on the programmer. Some type errors can only be caught dynamically, or both, or none of this. Yeah, so it's very simple, because if we don't have more constraint to follow, then we will be more smooth to write any code. So that's why if the language is weakly typed, then we will be happy that we have got some kind of program which I can write, and there will be less errors and it will be executed. And also we can dynamically check the errors and we can correct. Then the seventh one, type checking done by compiler is again type checking is static. Type checking is static. In last case, what I have told, that type errors can be caught dynamically, but type checking is done statically. uh, okay, this one, if the argument passed to a function call are such that the first and the third argument are integers while the second one is real, the type expression for the argument list can be. It's very simple. Yeah, it's C. First and third are integer and second is real. So that is type expression. So that is like T1, what is taught T1 and T2 and T3. So what you will take T1 cross T2 cross T3, and U1 will have three parts, U1, U2, U3, and these three we can just change with, we can update it with the types provided. So it will be integer, real, and this integer. Okay. Then this one for strongly typed languages. For 10th one, what should be the answer? No, no, not dynamic checking. Checking is only, type checking is static. So static type checking is done. In previous questions, I also mentioned that type checking is static in nature. So 10th A, there are some more questions. Type equivalence checks whether two type expressions are same or not, two expressions are same or not, two statements are same or not, or all of the options. For 11th. A, yeah, that is mentioned in the PPT. I think I should not cover it again. Then type of a statement is y dot type error or y dot type error or none of these. Yeah, that's C. Type of a statement may be void or there may be type error. Then this one, the type expression integer cross real, and that derives integer, and again maps this to a function which actually maps integer to real. So that corresponds to a function that takes an integer as a real and a real as argument and returns integer and a real, and all these four options. What can be correct? A, what it is telling, a function that takes an integer and real as arguments and returns an integer and a real. Hmm. No, 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 no. Just see what it is doing. It is taking integer and real as argument. That is correct. Then what it is returning? It is returning a function that is actually mapping this integer to real. Okay. So is there any option like that? So first is not correct. Then B is telling function that takes an integer and a real as argument and returns a real. No, here it is incorrect. Function that takes an integer and a real as an argument and returns an integer, it is also incorrect from here only. A function that takes an integer and a real as arguments and returns a function that takes an integer and returns a real. So it is actually a function that takes integer and returns a real. So that is actually D. Answer is D. Then this is the last one. Typecasting available in many programming languages is an example of. So what you can say about this? Hey, type checking. No, no, no. Not type checking. Actually, uh, when I started this lecture, there was one thing which I covered through that PPT. There was a term type coursing. So type coursing is actually where we actually try to um just solve that error, what we can say. So we are taking some of the type and we are actually uh, changing its type. So type coursing is we are correcting the type. So that is actually typecasting. So type coursing is typecasting. Okay. So answer is B. Okay. So this is these are the questions from the previous year. Now I will first go through the rest of the PPT. Then we will do some of the other stuff if time will allow it. Time will allow us, and we have lot of time. So let me share. Yeah. So this was one thing. Type expressions. So what is type expressions? That is what I had covered through the questions. That is same here. Like we can say there are two fields, length and word, and these all things are actually covered in the lecture. Then this thing, the last point, function maps a collection of types to another, represented by D maps R. D is a domain up to R, that is range. So that is actually there in the questions. So there was integer cross real was the actually domain, and integer provides or integer maps that real, that was the range. Okay, so function within that function. So coming to the next part, similarly these are the examples. If integer cross integer is character, so what it is telling that we will take two integers and then return a character value. Then if integer derives real to character, so real to character is also a function that maps the real type to character type, and that is actually range for this function, which tells that integer actually maps the value to the range, that is also a function. Then there are type systems. So it is actually a collection of rules that depicts the type expression assignments to program objects. So type checker is an implementation of a type system. Then there are types of languages. So types of languages is actually uh, if there are weakly typed, there are strongly typed, as you all know. So Compiler can verify that program will execute without any errors, and all checks are made statically. That is one thing, and that was in the question. Also called a sound type system. Then completely eliminates necessity of dynamic type checking. Most programming languages are weakly typed. Why? Because the programmers want that to be more friendly. Then strongly typed languages put a lot of restrictions. So there are cases in which type error can be caught dynamically only, and many languages also allow user to override the system, like in Java. Then there is type checking of expression. So we actually use a synthesized attribute type for that. So here, like for every expression, we have provided some action. So E derives ID. If we are writing like this, so what it will do, it will look up the entry for ID, and it will post it to E dot type. Then similarly for E1 operated to E2, and relational operator, and then bracket operator. So all these things are actually covered in the lectures. Then if there is some block, so nested D block, so there may be set of rules needed. Then there is a type of systems. um, then there is type equivalence, means there are two expressions S and T, so those are same or not, and that can be answered by deciding equivalence between two types. And then there are two kind of equivalences, name and structural. So these all things were covered for week 7. Now I will go for some of the numericals on parser again, because parsers were covered in first two lectures of this week, and type checking has no more, I think, uh, numericals or problems, because it is mostly theoretical part. So there was only one thing which I should cover, that if there are two different uh, kind of data type, uh, different data type values uh, for some expressions. So what happens that if like there is we have done like integer by float. So if we are using strictly typed grammar, strictly typed languages, then there will be problem. There will be warning or there will be error. In weakly typed, there may not be errors. So that is only thing which can be covered for type checking. Now I will go for some of the questions of parsing only. Now I am just staring. So let's do some questions on what things we have covered in parser. So starting with first and follow, this is just a kind of revision what I want to do. So let's consider a grammar. Grammar is like let me sit it down. So grammar is like S derives S and S or S or S or within bracket S or true or false. So the question is we have to just uh, tell two things. First is the first of S no there is you have to tell about first for each production and non-terminal. First for each production and non-terminal. So and second thing um, we have to tell why this grammar can't be parsed by LL1 parser. So these two are questions, the first and second. So if we do for first of each production and non-terminal, what we will get? So if we go for first of starting from this production as derives true. So simply I can say first of true will be, if we just say first of true will be just true, simply for this one first of false we will have false only. Then if we go for the third one that is if we collect it for this within bracket as what we will get, we will have this bracket in our first collection. Then if we go for first of S and S, what we will get first of S and S will be first of S only, so that will be first of S. So what is that? We have first of S is from third, fourth and fifth production we will have this open bracket, then true, then false and nothing else. So that is one thing. Then if we will go for first of S or S, that is also first of S, that is true, false, and the non-terminal here is only S, so first of S is already given. So the first thing is done. Then why this grammar can't be passed by LL1? This is the answer of first one. Why? Because first sets of one simple thing we can say, the first sets of productions intersect, like these two are same. So what we get, you can say like first sets of the productions intersect, and the grammar is, that's why, left recursive. Okay, so left recursive grammar, we don't have anything to change. It can't be passed by LL1 parser. So this is one. Now coming to the second question, there is a grammar like ABS, ACS, or C. So there are three things. First is compute first sets for each production and non-terminal. Second is why not LL1 like previous, and third is see what we say. We have to rewrite it so that it can be parsed by LL1. So starting from A, um, if I ask, it's so simple. If I ask for this each production, so if we consider this production ABS, what will be the first? You can write on chat section. Given Trosen, you can write it. I think it's very simple. First of ABS. So first of ABS will be, this is actually terminal, so A. Then if we consider next one, first of ACS, what we will get? Simply this A. Then if we consider the third production, first of C, that will be C only. And so these are for each production. Now there is non-terminal. So first of S, there is only one non-terminal, that is S. First of S will be from here A, from here A, from here C. So we have A and C. So these are things we have as first of production. So next thing, coming to the question number B, why it is not LL1? So from here what we can say, one reason is first of first set of, if we see ABS is equal to first of ACS, or we can say if we take intersection of these, so what we get, A intersection A, and that will result in A. So that is not phi, or we can say that is not empty set. So if anything happens like this, then we say this is not LL1, not LL1. Okay, if first of the productions overlap, then it is the easy check for LLL grammar. Then for C, if we want to write it like any other thing, so what we can write? So what we had, S derives ABS, ACS or C. So how we can write? We have to remove this problem of left factoring, I think. So what we get, we have A common. So S derives A S dash or C, where S dash will be BS or AS. So we had left factoring, we have removed it. Okay. Now it can be easily passed with LL1. Okay. Now there is third question, which has S derives SA, SC or C. So first I have to tell, or we have to tell, why not predictive parsing? One thing. Then the second is rewrite for predictive parsing. Then C is using first and follow build LL1 table. Okay. For the new grammar, rewritten grammar. Okay. So what will happen if we see for answering A, what we have? We can see here clearly that if we go for the simply like previous first of the productions, so first of SA will be first of SC will be first of S. What will be that? That will be C. So if we take just intersection of these, that will return us C only. That is not actually empty set. So that's why first sets of productions intersect. That's why grammar is left recursive, and we have to do something for that. So what we will do for answering B, we have S, SA, SC or C. So how we can change it? You can write it like CS dash, where S dash will derive AS dash or CS dash or epsilon. That is the thing, how we remove the left recursion. It was very clear because here from here also we can check there are two productions which have the same non-terminal which is there in left hand side. Now we have to just check for first and follow. So first and follow. We have two symbols, S and S dash. For S, what we have in first of S will be always C, and first of S dash will be, there is A, there is C, and there is epsilon. Then follow of S, follow of S is actually dollar, and follow of S dash is actually follow of S, that is dollar, and follow of S dash will be follow of S dash, and there is empty string, so that will be dollar only. So what we have to do, we have to create the ll1 table. So this is the second one. Now coming to the C part. So the new parsing table. How we will use, like this. We have S, L, we have A, not L, S dash. A, C, and dollar. So on first of this, FCL, then S dash derives A S dash, S dash derives C S dash, S dash derives epsilon. And there is another question. If we want to parse CA, how we will do? So like we have a stack, we will have input, then we have action. So in the stack, we will have on top of this is the starting symbol, that is S. On input we have CA, then dollar, so what we will do, we will just check this stack, and there is C. We will check this stack S, and there is C. So what we will do, there is this one, we will go to this one. So what we will do, there is a state FCL. What we will do, we will just pop S and push there LC. Okay, now we have dollar $LC, and we have CA, this one. Next we have C and we have C, so we have to pop. So we have popped it out. Now we have this L, ACA, dollar. From L and A, where we will go, sorry, not L, I've written L in my solution, there is a stress. So S dash and A, we have this one. So we will just pop out S dash and push. We will pop S dash and push A S dash. Means S dash A. Okay. So dollar S dash A, then ACA dollar. Again we have same. We will just remove it. We will have pop this A. Then we have S dash CA dollar, S dash and C. Again pop S dash and push S dash C. So we will have this thing, dollar S dash C CA dollar. We have this one. We have pop out, pop C. Then we have S dash A dollar. So S dash and A, we have S dash A. So we have to pop this S dash and push S dash A. So now we have this from here only. From S dash A, we will have this S dash A, then A dollar. What will happen? We will pop out this A. Now we have S dash and dollar. From S dash and dollar, we will go here. So S dash derives epsilon. So we have to pop S, and ultimately what will be there? We will have this kind of situation. Where we have dollar, we have dollar here too, and we will say it as accept. Okay, so this is for LL1. There is one more question on it. So let's consider the grammar. This is our question number 4. So there is goal derives expression. This one derives term plus expression or term minus expression. Next, what we have to do here is apply left factoring to create LL1 grammar. Compute first and follow for the modified grammar. And then using first and follow, build ll1 table. So these three are tasks we have to do. So first we have to create um, left factor grammar. So corresponding left, we're answering this A. So if we see this question correctly, so we have actually uh, three terms in the second production, second, third, and fourth, where term is actually used again and again. And then for term also we have the same condition. So we have to create two different variables or non-terminals which can take these values of term and factor and derive the next equations, or we can say productions. So first there is goal, that is expression, that is good, but from second onwards we should have term, expression dash, and expression dash will be plus expression minus expression for term. Also we have factor, then we should have another non-terminal we should introduce, and similarly what will be termed as should be term by term, or there should be epsilon, and for factor there will be no problem. So this is the left factor grammar. Now we have to calculate the first and follow. So we have these things, we should write it here only. So first of goal will be first of expression, then first of expression will be first of term, first of term will be first of factor, and first of factor will be num and id. Num, id, first of expression is like this only. First of term is num id, and this is num id. Then first of expression dash, what is that? That is plus From second production it is minus, from third one it is epsilon. Okay, similarly for this, the first will be multiplication, then this, then epsilon. Now coming to the follow of goal, as goal is not there in right hand side, so that will be always a dollar. Then follow of expression is the follow of expression dash, and follow of expression dash is again follow of expression. So there is nothing, there will be dollar. Similarly for this should be dollar. Then for term is followed by expression dash. So first of expression dash will be in the follow of this term. So plus and minus will be there again. Then if there is epsilon, then there will be follow of this. So follow of this will be, oh sorry, for epsilon we have dollar. For term dash is again follow of term from this one, plus minus dollar. For factor, what will be for factor? Factor, there will be factor is followed by this term here. So first of term will be there in the follow of factor. So multiply, then this, then from here factor of first of term, then for epsilon we will again go the follow of term will be plus, then minus, then dollar, and it is done. Now we have to create the LL1 table. Let's see, LL1 table or parsing table. So what we will have in our desk, so maybe a large table. So we have goal, we have expression, we have expression dash, we have term, we have term dash, we have factor. So we have num, we have id, plus, minus, multiply, this, then there is dollar. So we have to check for goal. Goal, there is the first entry, first has num and id. So what we will write, goal provides expression, goal provides expression. For expression has num and id again. So expression derives term expression dash, then expression dash has plus, minus and epsilon. For epsilon we will go for dollar, and so what we will write for plus, we have expression derives plus, expression dash. For minus, expression derives minus, expression dash. Okay, then for dollar, for epsilon we will have to go for, sorry, something is wrong, there is expression, I wrote it wrongly. Now for term, again there is first of term is num and id, so we will write term derives factor term dash, term dash, then term dash has a star, then divide, then for epsilon we have to go to follow, plus, minus and dollar. So let's fill the entries. So multiply will be there for term, derives multiply term, term dash derives divide term, then for all the other entries for follow we have term dash derives epsilon, term dash derives epsilon, then for this factor, and factor is also having first as num and id. From here, so we have for factor, for num, factor, for id. This is actually the table. Just done. This way we create the table. Now these are some of the LL1 parsing questions. Now I think we should type for LR parser kind of questions. So okay, we have just consider this question: S derives ABS or ACS or C. So first was to do compute follow of S. Okay, and second compute canonical set of LR 0 items and the last is I think okay, we have 5 questions here. The third is we have to build X and go to table. using LR0 plus follow. The next is it is SLR 1 or not, that we have to comment, and then we have to parse ABC. So let's get started. For A, we have a follow of S. Follow of S is follow of S from here, and follow of S is nothing but dollar. One thing is done. Second is we have to create the canonical set of LR0 items. So let's start from augmenting the grammar. So we will have S test derives S, and with this pointer, then pointer is before S, so we will just use the productions as have. So these are dot abs, acs, and dot c. So these are the things all done. From here we have got state 0, or we can say I0 also. Okay, next on capital S, where we will go, where we will have only one production. So state 1. Next we have small a, we have two productions here. A S derives a dot bs, S derives a dot cs, and on C, that is state 2. On C we will go to S derives c dot, that is state 3. So state 1 and 3 are looking good. We have to go for the state 2. State 2 we have B, which will lead us to A B dot S, and S will have again these productions A B S, A C S, and there will be C. That is state 4. For C, similarly, AC dot S, S derives dot ABS dot ACS dot C. That is state 5. So if we will go for so state 2 is done. Now state 4. State 4 we will, if we will go for this S, we will have S derives ABS dot, that is state 6. And if we will go for A, we will ultimately get S derives A dot BS and A dot CS, that will be state 2. And on C we will at state 3. Simple. State 6 is done. Now coming to this one, state 5, S derives CS dot. On A, again it will go to state 2. On C it will go to state 3. So this is done. I think something is missing, because my solution is showing there are 7 states. I have got only 6. Where I am mistaken. So A we have A and C. From state 3, state 2 we have A dot BC. Then on B we went to state 4. Oh, I haven't written this name state 7, so we are right. Now we have this, then this first and second, we have now third. Action go to table with follow. So we have state action go to for go to we have just one thing, that is s, and for action we have a, b, c and dollar, and we have 8 states. So on 0, on state 0, s we will go to state 1, and on a we will shift to 2, and c will shifting to 3. So s we will go to yes, we are going to 1. On a uh, we are shifting to 2 and 3. Then state 1 is done, and state 1 on dollar we will accept. On state 2 sorry, on state 2 we have on b we are shifting to 4, on c we are shifting to 5. So s4, s5, 3 is actually a reduction, so we have to number the rule. Oh, so let's say this 1, 2, 3. So we have done the third rule, so we will reduce with 3, r3. Then we have this fourth one, fourth state. On s we are shifting to 6. Then on a, sorry, going to 6, and on a and c we are shifting to 2 and 3. So s2, s3 and 6. For fifth one, again shift, going to 7 and 2 and 3. Then on 6 it is actually done for first production ABS. So R1 will be on the follow, that is there, and similarly for this 7 we have follow for second one, R2. Okay, so is this SLR1? Yes, it is SLR1 exactly, because there is no shift reduce conflict. Okay, so that's D is done. Now we have the final one, that is the question number E. We have to parse ABC. Okay, so how could we do? Okay, remaining input or input buffer we say, and there is action. So on stack we'll start from 0, and we have this ABC dollar. So 0 on dollar, sorry, 0 on A, we have 2 S2. So we have shift 2. Okay, so what we will do, we will just put A on top of it, and the state we have cited, and we will remain with BC dollar. Now 3 and B, 3 on B, oh sorry, 2 on B, 2 on B, 2 on B, we are shifting to 4. Okay, so we have S4. We will again do the same thing, 082 B4 and C dollar. Now 4 and C, let's see, 4 and C, I have done something wrong. Yeah, okay, on B I have done it. It's wrong. We have S3. So 082 B4 C3 dollar. Now we have 3 and dollar, 3 on dollar, we have R3. So R3, we will just pop out the two characters on top of it, 082 B4, and push the S, that is left hand side. Okay, and we have dollar. Now S and dollar, we on S and dollar we have to, and also we have to put the string on 4 and S, that is this 6. So we will go to 6. Now 6 and dollar, 6 and dollar, we have R1. So we will again remove these 4 ABS. We will just we remain with ABS we have, and we will remain with S only, and dollar. Now we will go to 1. So 0S1, and dollar 0S1 and dollar, that means it is actually accepted from here. So that is a question done. Now there is another one, question number 6. Is there is SA, SC, or C? canonical set of LR one items. Then action go to table. Then third is whether it is LR1 or not. You have to comment on it. And again we have to parse kaka. Okay, so let's start the things. So first is canonical set of LR1 items. So for that, s-derives.s, s-derives.sa dot s-derive.sc and s-derive.c. That is I0. From here on S, we will go to s-derives dot. That will be I1. On S, we will go to s-derives s dot a, s-derives. Oh, I think I have done wrongly. Sorry. There are three things after S now. So it is incomplete. S derives s dot a, s derives s dot c. Now it is done. Now on C we will go to s derives c dot. That will be I2. Then from here on small a we are going to s derives sa dot. I3 on C s derives sc dot. I4. It's a very small question. Wow. So we are done with this graph or canonical set. Now we have to create for we have to go for this action go to table. Let's say there are actions. There is go to will be there for S only. We have only 5 states 0 1 2 3 4. On action we have A, C and dollar. Just write it. Let's write it. So what is on 0 on S we are going to 1. So and on C we are shifting to 2. On S I1 on small a we are going to 3. We are shifting to 3. On C we are shifting to 4. No, it's not actually shifting, it's reducing. uh, uh, no, wait, again wrong. Okay, on 1 there is one thing we have to shift to 3 4 and there is on dollar it will be accepted. Oh, it's right, I was doing that. Then on 2 is actually I should provide this number 1 2 3 on 2 we have done with third production R3 R3 R3. Then on 3 we have 1, so R1 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 and for 4 we have R2, R2, R2. This is the second one, this is the first one, and this is the third one. So our table is done. Now we have to parse this string kaka. So for number D, what we will have, we should have stack, we should have input buffer, and then action. Oh, what is happening here? Again, it's hanging. Okay, now fine. So we have CA dollar, and we have on top of stack that is 0. So 0 and C, let's see, 0 on C we are shifting to 2, so there will be S2. So what will happen, we will push this C on top of it and the state number that is 2, and we will have ACA and dollar. Now we have 2 and A. What will happen, 2 and A, there is reduction R3. So what will happen, on R3 the left hand side symbol will be pushed on this and these two will be popped out. So S, okay, and 0 on S, what we will get, 0 on S we have 1, so we will push down 1 here, we will go to 1, okay, but should be our next step. I am not skipping it. That's done. What I have done, I have just done R, what was there, R3, okay. Now we have ACA dollar, we will go to 1. So we have request 1 ACA dollar. Now 1 and A, 1 and A, we have S3, so we will push it, we will push A, and the number of state 3, we remained with CA dollar. C and C we have reduced using 1, so we have R1. R1 we have to reduce A, we have to just pull out this till state 2, and we will push S only. So R1 is AS, so we will pop out this SA, means mod of 2 into 2, that is 4 values we will pop out, and we will push the left hand side symbol that is S here, and we have CA. Now S and 0 we will go to 1, so we will use 0 as 1 CA dollar. Okay, now 1 on C, we have as 4, we have to shift on 4, so 0 as 1 C4, and we will be remained with A and dollar. Okay, now 4 and A, 4 on A we have R2, reduce using 2, which tells there is SC. So we have to pop out this S and C, and we have to push S on top of it. 0 S, A dollar. Now we have to go to 0 on S, that is 1, go to 1, so we will push 1 on top of it, $8. Now A and 1 and A, one and A we have S3, so 0 S1, A3, and we will have dollar on top of it. And 3 and dollar we have R1, that is SA, so we will pop out 4 symbols, and we have R1. Now we have this 0, and we have pushed 1. Now we have dollar on top of it, and S, so we have to go to 1, 0 S1, dollar, inputs are done, so 1 on dollar we can say accept from here. So that is done. Kaka is actually passed. So this is a simple question. Now I think my pages are finished. Okay, I will check. I am checking for some smaller questions. I have it. And actually questions are very similar. We get let me add some pages first, then we will do, I think, today's last question. Now consider this grammar question number, I think 7, as derived as A or A. So we have, there is only one question, whether it is LR1 or not and SLR1 or not. So for SLR1 parser we have to first compute the follow. So follow of stats will definitely be dollar. Follow of S will be dollar, and from here this semicolon. Now just go for canonical set of LR0 items. First we have to augment it. We written it previously, yes. So it's I0. From here where we can go, if I say S, so S will definitely take us to S dash derives S dot, and derives this, and the I1. Then on A I will go to S derives A dot, it is I2. Next is we go for comma, we will go to S derives S comma A. This will be our I3, and from I3, just a second, on A we'll go to S A dot, I4. So this is one thing. Now we have to create the LR1 table. We have two symbols and $1, 3, and only one go to. And we have 5 states starting from 0 up to 4, 2, 3, and 4. So 1, 2, 3, 4. Now what I have to do? A comma semicolon, sorry, and dollar. So on 0, on S we are going to 1. Okay, on A we are shifting to 2. On 1, on dollar we are accepting it. On 1, on semicolon we are shifting to 3. On 2 we are actually reducing, so I can write it 1, 2. So R2. Okay, on 3 we are shifting to 4 on A, and on 4 we are reducing using 1, R1, R1, R1. So it is LR0 definitely. Now coming for SLR1, what will happen? SLR1 we have dollar and comma, so the reduction will happen on these two only, this dollar and comma, sorry, semicolon. So again there is no dispute, there is no problem, so it is also actually SLR1 only, SLR1 also. Okay, so it is both. It is done. Still we have some time left, around 10 to 14 minutes. So let's search for some small question. So this is a small question for LALR1. So we have given some LR1 items. State one is left. So we are given four states. First is A derives dot A B. So we have to tell about um, where we can get shift reduce conflict. One thing, and LALR1 parser which states will be merged. Mm, and again from here, if there will be reduce conflict. Yes, these three questions. So shift reduce conflict where we can get just see in state 1 there is no problem, 2 there is no problem, but if we see this state 2, so what will happen, we have we will be shifting using this A derives dot A comma C, and then also we have reduction using this B derives A dot and A. Okay, so for say it's 1, B and C. So A, how we can comment in state 2. What we are getting, A derives dot A comma C, and B derives A dot comma having SR conflict. Then for B, which states will be merged? If we see the states 0 is actually same, having different look aheads. So states 0 and 2 can be merged, will be merged. For LALR 1. Then if there we will merge it, will there be reduce conflict? I think yes, because if we see we have two things. There is A derives A dot comma B and B derives A dot comma B. Those two will come together. So that's why there will be RR conflict in LALR 1. Okay, so I think it's done. So these are some questions we have solved today, a lot of questions, and these are the numericals, previous year questions. So thank you. Now I will just wind up the things once more, just revising the things in the next 5-6 minutes which are remained. So first I went for this course PPT where we just went through type checking and semantics and all the other things which were taught in the lectures, and those were basically about how we can do a type check, how we can specifically pose some rules which may be strict, which may be uh, not strict, but ultimately what we have to do, we have to actually um, provide some of the rules to the language uh, with which either it can semantically just check for the things whether it is going correctly, or it can correct it also. If we are just checking it, we tell it as type checking. If we are correcting it also, we will tell it as type coursing. And type coursing is also typecasting, which is used in most of the languages. One thing. Then the I think my oh, yeah. So this is one thing, and the next thing is we can actually uh, go for type expressions. So what type expressions tells where we are using some of the types with provided non-terminals, or we can say uh, if there are any two anonymous things, then we can pose some of the types there. So if there is one is integer, one is character, we can do something like it can take integer and character and apply some rule or operator on top of it, and again uh, after applying it, what we do is we actually um, uh, take a function which can actually map some values to some ranges of values. So one thing is domain, one thing is range. We map the things from domain to range, and at last there are some type checking systems or type checkers uh, which actually checks the type. So, and there is type equivalence also, which actually checks whether types or two types are equivalent or not. Then we went for some of the previous year questions about it. uh, so in previous year questions we found that mostly are there are most of the questions which are actually theoretical. So in this question we just saw how it can take a function as a domain and return a single value integer. Then there are weakly typed and strongly typed programs. So what we do in these things, in weakly typed we have a good uh, we can say communication for what we want to write. We have good idea, we can write it easily. But if we go for strongly typed, the language may be strict, but the problem the good thing is that it can take less time, and also it is less prone to the errors. Then if we have some additional code, we do it dynamically. Type checking is done semantically, and most programming languages weakly typed, what I have told earlier. Type checking is always static in nature, and then like this we have three things we can write. We can apply the in any type of on top of it. Then strongly type or type languages uh, uses static type checking on compile time mostly, and type equivalences, two type expressions are same or not. Then the type of statement may be void if it is not returning anything, and or there is some error if it is returning some error. Then there is what I told about mapping. So if there is some operation applied on two things, that may be domain, that may be range also, but here there is domain, and the mapping function, mapping is also, or range is also a function which is mapping some integer to real. Then there is typecasting. What I told, type coursing is same as typecasting. It is used by some programming or most of the programming languages. So that is all for today from my side. If there is any doubt, and thanks Revan for joining it thoroughly till the end. So I will be finishing this lecture, and the lectures will be uploaded uh, just after this class. And if there is any feedback, yeah, Revan, thank you. So if there is any feedback, anything you want to ask, you can just reach to this um portal, discussion forum, and the videos I have uploaded. So thank you all for joining. Okay, Revant, thanks. I am ending this call.